Welcome back to the ROS lecture series. This is part 3. So to start off with, we're going to look at packages, and a package is a basic unit of ROS. A package includes code, data, and documentation. The package contains one or more nodes, okay, and we saw nodes in the last lecture series, or it can include configuration files for running other nodes. The number of official packages is about 1,500 for ROS Kinetic. In addition, there are more than 4,600 packages developed and released by users. Now, each ROS package must have a CMAKELISTS.TXT file and a PACKAGE.XML file, and we're going to have a look at these in detail in a little bit. Now, the other thing is that packages must be in their own folder. This means that you cannot nest packages, and you can't have packages that share folders. Now, packages should also be stored in the Catkin workspace, which we created in part 1 of this lecture series. Okay, so now looking here, we've got our workspace folder, and this is the one that we would have created in lecture 1. However, this is after we run a make, and we'll have a look at that a little later in the lecture. What we have here is the build, the devil, and the source folder. And the build folder contains the build related files. The devil contains the message, server header files, and user package library, and also the executables. However, the most important folder here for us is the SRC folder or source folder, as this is for the user's source code. So this means that you can save and build your own code in here. Now we're going to have a look at creating our first package. So firstly, ensure that you are in the source folder of the Catkin workspace by changing into that directory using cd. And you can see this on the slides in the terminal. From there, you can use the command catkin create package, and that will create a package. The first argument for this is the package name, which in the example in the terminal we can see the name first package was used. Further, there may be dependencies on which the package will depend, and these can be added as further arguments. In this example, we have the dependencies standard messages, ROS Python, and ROS C++. So once we have created our package, if we go and have a look in that folder, in the source folder we'll have a folder called first package, and this is what's inside of that folder. You'll notice that we have an include folder where we'll have our headers, we have a source folder where all of our code will go, and we have the CMAKELISTS.TXT and the PACKAGE.XML files, which is what I mentioned earlier each package must have, and these are automatically generated, but you may need to edit them for your purpose. So now let's have a look at the package.xml file. So this file, as I said before, must be included with every package and must be in the package's root folder. Okay, and we saw this in the previous slide. This file provides documentation on the package, and it includes information like the name, version, authors, dependencies, etc. Now, with this, you need to be clear, because this is so that other people can read what this package does. So for example, you need to be sure that you list the system package dependencies on what your system will work on, because when you give this to someone else, it will not work if they don't know what packages are required. So let's have a look at the basic package.xml file to start with, and then we can add some more information to it. So the basic structure starts with the package tag, and we've got this as the first line here. You'll notice that it says format equals 2, and this means that it's a different format than ROS used to use, and all old formats are out of date and are recommended to be updated. So for your package.xml, this is the minimum that you must include. So you must include the name of the package. Okay, so we've got first package, this is what we created earlier. You then need the version, okay, which has to be as 3 dot separated integers. So we've got 0.0.1 here. We need a description to describe what the package does and contains. So we've got a short little description there. Then the maintainer, which is the person that's responsible for maintaining the package. So you've got their name and their email there so that people can get in contact with them if needed. And also the license that is used. And you'll have to do some research on this if you want to release your package such that it's used appropriately within your license, and if you're dependent on other licenses. So another thing that is included in the package.xml file is the dependencies. Now there are 6 types of dependencies. Firstly, we have the build dependencies, which are packages that are needed to build the package. Secondly, build export, which are the packages needed to build libraries against the package. We have execution dependencies, which are packages needed to actually run or execute the code for this package. We then have test dependencies. So this is when performing testing on your package. You may need specialized packages for testing the package, possibly for unit testing. We then have build tool dependencies, and these are build system tools that the package needs to build itself. Okay. However, you should really only need catkin for this at this stage. And lastly, we have documentation tool dependencies, which, as the name states, it's for packages for documentation. So let's continue and have a look at a more complete package.xml file. So we can add the dependencies to our example. We have, under the author in the middle, you'll see build tool depend, which is catkin. Okay, so that's our build tool that we're using, and for us it's always going to be catkin for right now. And then we have build depend and execute depend for the 3 packages we added when creating the package. So remember, when we created the package, we added those 3 dependencies as part of the arguments. So this means that basically to build this package we require these 3 packages, And to run this package, we require these three packages, which are the ROS C++, the standard messages, and ROS Python. Now you'll notice also that I added some extra optional tags here. These aren't required, but you can put them in if you feel like it, and you need to. So a URL, which allows you to link to a website or a page describing the package, and also an author tag, as the maintainer may not be the same as the author. As said in an earlier lecture, the ROS build system uses CMake, which is cross-platform make. And the CMAKELISTS.TXT file describes how to build the code and also where to install it. The CMake that is used is ROS specific as it is modified. The reason ROS uses CMake is it allows ROS to be built on any platform, for example Linux or Windows. Further, if you use Qt or Visual Studios, it is supported, so that can be helpful as well. So now let's have a look at the CMAKELISTS.TXT file. So what must the CMAKELIST.TXT include? Well, this is actually going to depend on what language you use, your dependencies, and some other things that you're going to have to research. But for basics, given the example here, we have the first line, we have the CMake minimum version. This needs to be version 2.8.3 or greater for Catkin, and so if it's not, you just need to update your version of CMake. The second line is just the package name, okay, which we gave it before when we created this package. The third line is find package. This is the packages that are dependent, and this installs the dependent packages if they can be found, and if not, there'll be an error. Now these are all the three packages that we said were dependent beforehand. We've got ROS C++, ROS Python, and standard messages. On the fourth line, we have Catkin package, which gives options when building on Catkin. In this example, we are just specifying the dependent packages. We then have include directories, which basically says which folders should be included in the build. And to specify the header folder that we saw earlier in our folder, we can use Catkin include directories. We then can specify the executable to be created, so the thing that actually runs, and these will be our nodes. So here is where your code that you have written comes in. So this is going to take your code, compile it, and make the executable, like most of you have done with other programming languages. So in this example, we have the executable name first node. Okay, so that's the thing that runs. And to make that executable, it will use the code called first.c++ in our source folder. We will look at this code a little bit later. Lastly, here we have target link libraries, and this links libraries that are needed before creating the executable. In our example, this is our first node and the Catkin libraries. So now we're going to have a look at some code. Now, in this lecture series, we'll be not teaching how to program in ROS at this stage, because every student will have different experience with different programming languages, and it's not expected that you know these languages in this subject. But maybe later down the track, we can look at adding some lectures on some programming. So ROS allows many languages to be used for the source code, including Python, C++, Lisp, Java, C#, Lua, Ruby, etc. There's quite a lot of languages that you can choose from. However, for learning how to use ROS, I'm going to recommend that you use C++ or Python, as there's a lot more tutorials and resources and documentation for these languages for ROS. However, as I said, you will still need to understand the language at its basics beforehand. Now, with the code that you write, ROS expects that you use SI units, so meters, kilograms, seconds, etc., etc. You should all be familiar with these. And this is important to ensure that your code and messages can communicate with other packages without the need for conversion, and also to reduce the possibility of errors. The next thing with your code is it must follow the right-hand rule for your X, Y, and Z coordinates. And you can see this on the slides here. Meaning, using your right hand, as shown, gives the positive direction on all the axes. So the positive direction for the X, the Y, and the Z. This also applies with rotation. With positive rotation around the axis will follow the curl of your right hand. And you can see this on the lecture slides as well. Now, this can cause a lot of problems if you do not follow this convention when talking to other nodes, especially when you're using other packages that are not your own. Another thing with code is to follow proper programming style. This goes for anything you do, but ROS does have its own conventions for each language, and you can look this up on the wiki when you choose which language you're going to use, and it ensures that your document is readable and consistent throughout ROS. Alright, now we're going to go through some C++ code that I've put together, and this is very basic. But I put this together to understand what a node is doing at the very basics. Now, the first thing to note is this is a publisher node. So, looking at the start of the code, we start with some includes. We have ROS.h, which includes most of the commonly used features of the ROS system. And then we have standard messages /int8. And this will help us in defining a message using an 8-bit integer. After this, we have our entry point function, or our main function, which most of you should be aware of. And then we have ROS init, or ROS initialization, which initializes ROS, which specifies the name of the node. We then have the node handle, and this will run the node initialization and also clean up the resources when ending the node. We then have a long line here, which is very important. We have the publisher. So this tells the master that this node will be publishing a message of type 8-bit integer on the topic named first topic. Okay, so this is a publishing node. Okay, so it's going to be sending messages out, and those messages are going to be 8-bit integers, and they're going to be on the topic, first topic. So subscribers could subscribe to the topic, first topic, and they will receive 8-bit integers if they were to connect to this. At the end of this line, you'll see there's a second argument, and it's 1,000. So the 1,000 is the size of the queue. So basically, this means that it'll allow up to 1,000 messages on the queue before throwing old ones away. So this would only happen if we're publishing too quickly and the buffer starts filling up. So either we need to slow down or we could increase that value. Now the other thing that we get by running this line is we get the object named firstPub, which we will use in our code a little later. On the next line we have rate and then this call loop rate, and this sets the frequency at which we want the node to loop at. And here we have 10, which is 10 Hertz. So basically the code will run and then it will sleep until the next loop, such that we have a loop rate of 10 Hertz. Now what's good about this is that it means that we can guarantee that our code will be running every 100 milliseconds. So we know exactly the rate at which it's sending out messages or doing some operation. We then have our while loop, and it'll continue while ROS is okay. So this means it'll continue whilst the program has not been stopped or terminated. So in here we have a very basic message of an integer, and then we publish this message using our first pub object. Okay, so we use the method publish and pass the message. Now all we're doing here on every loop is we're incrementing this count variable. Okay, so the first message should be 1, the next message will be 2, the next message will be 3, and so on and so on. Now you'll also see this ROS info, and it looks very similar to printf, and you can think of it just like a printf. And all this does is just allows us to see what's going on. Okay, and because at the moment we can't see these messages, we'll have a look at looking at messages a little later. So this will just print out the message directly to the screen for us to have a look at. So next we have this ROS spin once. Now this is only really necessary if we're to add a subscription into this program. So basically make it subscribe to something, a topic, and this is so that the callbacks would be called. It isn't really necessary for this program, but we just add it just so that it's there, just if we do add a subscription later. Now the last thing here is our loop rate.sleep. So basically what this does is it will sleep, the program will sleep for the remainder of the 100 milliseconds in the loop, such that we ensure that we have a 10 Hertz loop rate. Once everything's written, we can now build. So firstly, you just need to change into the Catkin workspace. Okay, so at the top level of the Catkin workspace, and then you just run the command catkin make. When you do this, it may take a little while to compile everything, depending on how large the code is, and it will tell you if you have any errors in your files or in your code, and if you do, then you need to go back and fix everything, and if not, then you can start running your node. So let's have a look at actually running the node. So the first thing that we have to do is run the master. So to run the master, we use ROS core, and you can see this on the left hand side of the slide. Okay, so we can see it all start up. If there's any issues, it will tell you that there's some issues, okay, and it can't start the master. But if it's working, it should look something like this. On the right hand side, we've opened up a new terminal and we can run our node. And to do that, we use the ROS run command. So this has two arguments, the first being our package and then the node we want to run. And we can see the message that's published. And we're seeing this as we had the ROS info printing to the screen. And so you can see this 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. And this would be the message that's being passed through the topic. Alright, so now that we've looked at packages, we have built a small package and we've run it. In the next lecture, we'll look at some ROS commands that we can use with our nodes or other people's nodes, and packages and some commands we can use for communication. Thank you.